A super important thing to understand in chemistry is units. You really need to master units in order to be able to do the calculations that are going to be part of the course throughout the course. So I would say that units, you have to make them your friend. And I mean that. You really need to make them your friend. You need to become conversant with them. You need to understand them. You need to know them. So the first question we might want to ask ourselves is, how do we measure things, in what units, and what are the kind of things we measure? So you can easily imagine the kind of things that we might want to investigate, things like time, temperature, size, volume, mass, speed, or distance. And it's also worthwhile keeping in mind that anything that can be measured has both a number and a unit. So we could have 1 milligram, or we could have 5 milligrams, or we could have 100 meters, or we could have 500 meters. The list goes on. The possibilities are almost infinite, but we do have this combination of the unit itself and the actual number. The unit is super important because it will really define the length. 95 microliters is going to be, or the volume, or whatever it is, 95 microliters is going to be a very different volume than 95 liters. So the units really determine how much you have. In order to convert one number in a certain kind of unit to another number in a certain kind of unit, we have to understand equalities. Now, in most countries around the world, the metric system is in operation. So we have things like kilometers, liters, kilograms, and so forth. In the US, we're a little behind. We're still not with the metric system. So instead of kilometers, we're using things like miles. This is a little silly, but it's the way it is. So we have a bunch of equalities in the US, in other words, 1 foot equals 12 inches, that don't exist in countries like France or pick any country in the world, really. They're on the metric system, we're not. So it is nonetheless useful to understand what equalities are in terms of the US system, and then be able to actually convert between metric and US. So for example, if we wanted to go from centimeters to inches, we could say that 2.54 centimeters equals 1 inch. Or we could say, as highlighted here, that 1 kilogram equals 2.2 pounds. That means if you know what you weigh in pounds, you could use this equality to convert your weight to kilograms. Equalities set us up so that we can create conversion factors. If we say that 0.6214 miles equals 1 kilometer, which is absolutely true, these quantities are, of course, equal to one another. If we set them up in a ratio with 1 kilometer on the top and 0.6214 miles on the bottom, this by definition equals 1 because these two quantities are absolutely equal to one another. If we were to flip things and we were to say 0.6214 miles over 1 kilometer, same situation, they're equal. So the ratio of the two things is 1. Now putting these in conversion factors is useful because when we have it in this form of 1 over the other, then when we go to convert, let's say, as we see here, something from miles to kilometers, we can ensure that our units cancel and that we get the right answer. So here our starting quantity is 26.22 miles, and we multiply it by a conversion factor, and we make sure that miles are in the denominator so that they will cancel with the miles in the starting quantity. And that's going to give us this number, which is 42.2 kilometers. So you can see here that in kilometers we have almost double the amount. Not quite, but that makes sense because there's fewer miles in 1 kilometer. We're now going to address units of measurement in the metric system and the SI system. These are used for things like length, volume, mass, temperature, and time. As I commented previously, this is what's largely in use all over the world, and certainly for science, no matter what kind of science you're talking about, these are the systems in use. Now, the metric system and the SI system do vary slightly. Sometimes the standard, what we call the standard measurement, is the same. So in other words, for length, in the metric system, the standard measurement for length is the meter. And in the SI system, it's the same. In some cases, things vary. The standard unit for mass in the metric system is the gram, and in the SI system, it's the kilogram, and so on. You don't have to memorize these, but you should be familiar with the types of units that are in play here, and you should understand them. We're now going to move on to how we can use prefixes in the metric system to determine the size of a unit. We have a whole series of prefixes that derive from the Latin. So we have things like deci, centi, milli, micro, nano, pico, and femto. Notice that as we progress through these prefixes, the unit is getting smaller and smaller and smaller. So what does that really mean? Well, let's say, for starters, with deci, let's just arbitrarily say that our reference point is the liter. And when I say arbitrarily the liter, I mean we're not talking about meters or seconds or grams. We're just choosing the liter. If we say it's a deciliter, that means by definition it's 1/10 of a liter. That can be expressed in different ways. 1/10 is also equal to 0.1 or 10 to the negative 1. So as you see here on the right, we can say that 1 deciliter is equal to 10 to the negative 1 liters. Now, centi will break up our unit into even smaller pieces. So now we've switched from liters to meters, but the principle is still the same. It's gotten even smaller than the deciliter. A centiliter is 1/100th of a meter, as we see it here. Again, that can be expressed as 0.01 or 10 to the negative 2. Here we say 1 centimeter is equal to 10 to the negative 2 meters. If we go on down the line, we see each time 1 millisecond equals 10 to the negative 3rd seconds. Notice up to now we've just been moving up by 1 exponent each time. We make a jump with micro. Micro is getting really small. 1 microgram equals 10 to the negative 6 grams. I'm not even going to try to express that fractionally, but you can see it's getting very, very small. And then we jump by another a difference of 3 between our exponents, and we see that a nano is super tiny. It's 0.000000001, which is 10 to the negative 9th. So 1 nanometer is 10 to the negative 9th meter. We would have to chop our meter up into really tiny units to get a single nanometer. Now, you might have noticed here that for every time we said, let's go back to centimeter, that 1 centimeter equals 10 to the negative 2 meters, it follows that in 1 meter there are 100 centimeters, because we're dividing that meter up into 100 centimeters. On the flip side, we also have prefixes that do the opposite of making things get very small. We get things that actually increase the size of the unit. So I'm going to focus on the bottom here first, because I think you're probably more familiar with things like kilometers. 1 kilometer means, if we express it in terms of meters, that there are actually 10 to the 3rd meters in 1 kilometer. So we've actually kind of made things large. We've expressed 1,000 meters in a single unit, so it's larger, right? We've increased the size of the unit. Now again, we could flip this around, and 1 meter is going to be equal to 10 to the negative third kilometers. For the purposes of this course, I'd like you to know mega and kilo. You do not need to concern yourselves with gigatera or peta. In summary, here's a good table that will give you what you need to know. And I've highlighted from nano, which is something that makes things smaller, as we discussed, up through kilo, which is something that would make a unit bigger if we're using, let's say, a meter as our reference point. So you have to memorize these. You have to know what the equalities are and be able to go back and forth between, let's say, the meter and the kilometer, or the centimeter and the meter, or do this also for things like grams or whatever other unit we're talking about, seconds. Doesn't really matter what it is. It's important to keep in mind that these prefixes do the same thing to whatever kind of unit you're talking about. And again, I just want to remind you, or maybe put this a little differently. So let's look at this important note. If we're expressing a single smaller unit in terms of a larger unit, in other words, if we're saying, okay, we have 1 millimeter, and we want to make an equality for that in meters. Well, a 1 millimeter is clearly a tiny part of a meter, so that's going to equal 10 to the negative third meters, or 1/1000th of a meter. Notice that when we are going in this direction from a single smaller unit to a larger unit, our exponent is negative. Now we can, as always, do this the other way around. If we want to take our 1 meter and express it in terms of millimeters, this means we're going from a single larger unit, 1 millimeter, and we're expressing it in terms, or we're making it equal to a smaller unit. Well, it follows that that has to be a large number. That has to be 10 to the third millimeters. The interesting thing to note here is our equalities are in both cases are between the same units, a millimeter and a meter. We're just, in the first case, using 1 millimeter, and in the second case, using 1 meter. Notice that the absolute value of the exponent is the same, 3, but in the first case, it's negative, and in the second case, it's positive. I think it's a little easier when you're starting out to think of 1 meter as 10 to the third millimeters than thinking of 1 millimeter equaling 10 to the negative third meters. When we get into conversions, you're going to see that you can use either one of these and get the same answer as long as you have things set up correctly. The main point is to not get these two things confused, and that's going to take a little practice on your part. It does help to visualize. So what I just explained, this 10 to the third in some cases and 10 to the negative third in other cases, I think we'll see it a little better if we look at this 1,000 milliliter graduated cylinder. So 1,000 milliliters is equal to a liter by definition. And clearly, if we're going to take a liter and we want to set it equal to how many milliliters, it's going to be 1,000. 1 liter equals 10 to the third milliliters. If we're going the other way around, and this is the one I said can get a little more confusing. If we want to say 1 milliliter is equal to how many liters, then we have to start going towards this small fractional amount. So look at the graduated cylinder. Think of how tiny a milliliter is in terms of this whole volume. And I think you'll see that if you're going to put it in liters, you have to say 0.001 liters, or 10 to the negative third liters. I have one more example in this regard, which I think makes it even more crystal clear. I mean, I'm hoping it's crystal clear to you. Let's say we have this long stick and it has, it's a meter in length. And we want to take 1 centimeter and express it or make it equal to meters. You can see here that 1 centimeter, based on this little division, is equal to 1/100th of a meter. That's 0.01 meters. So that means 1 centimeter equals 10 to the negative 2 meters. Visualizing this stuff really helps. Now, the flip side, once again, is 1 meter equals 10 to the 2 centimeters. 1 meter equals 100 centimeters. That's pretty obvious, right? We can see that right away. The reason I am emphasizing this to such a degree is I've taught chemistry for a while now, and I do see students getting this mixed up quite frequently when they go to make these equalities and then conversions. A lot of times students will get the sign of the exponent wrong when they try to, let's say, they might say 1 centimeter equals 10 to the 2 meters. That would be completely wrong. So you definitely want to avoid that situation. And it would be good to do some practice. Practice with millimeters, micrometers, nanometers. Express them both ways. Take a millimeter, see what it equals in meters, and then do the other thing around, take a meter and see what it's equal in terms of millimeters, and do it for the other units. Practice will help you enormously. Now we're going to use what we have learned so far to apply equalities and conversions to three-dimensional objects. Let's focus our attention on this square or cube here on the left. And the first thing we want to pay attention to is if we want to get the volume of this cube, we need to multiply 10 centimeters times 10 centimeters times 10 centimeters, because that's the length of the side of our square, right? And that's going to give us 1,000 centimeters cubed. It's worth noting that if we were to sort of pull out a tiny centimeter cube from this box, that volume, also following the same logic, would be 1 centimeter cubed, or 1 centimeter times 1 centimeter times 1 centimeter. Just so happens, and this is something you just need to learn or memorize, 1 centimeter cubed equals 1 milliliter. Now it's of interest to note that the total volume of this square is 1,000 centimeters cubed, and that 1 centimeter cubed equals 1 ml. I think you can see that that means that 1,000 centimeters cubed would equal 1,000 ml, which in turn equals 1 liter. We're now going to use this three-dimensional space in order to set up an equality between centimeters and decimeters. And we want to be able to set up an equality because at some point we're going to want to be able to convert volumes, cubic volumes, into from one unit to another unit. Let's say we want to convert something from centimeters cubed to decimeters cubed. Well, we need our equality that we can make into a conversion factor. So here we can see from the bottom of the square that 10 centimeters equals 1 decimeter. That means that if we square the sides, if we do 10 centimeters times 10 centimeters times 10 centimeters to get the volume, the cubic volume in centimeters, that is going to equal 1 decimeter times 1 decimeter times 1 decimeter. And then we're left with the equality 10 to the third centimeters cubed equals 1 decimeter cubed. This is very useful to have because we can use it to convert a given volume from centimeters cubed to decimeters cubed. So here's a sample problem. Convert 253 centimeters cubed to decimeters cubed. Well, we use the equality we just defined above, and we say 253 centimeters cubed times 1 decimeter cubed over 10 to the third centimeters cubed. Notice that our centimeters cubed cancel. we're left with decimeters cubed, and we get an answer of 0.253 decimeters cubed. The object lesson here is when we're setting up an equality for a cubic volume, we have to cube the length as well as the unit. So in other words, that 10 centimeters, it's 10 to the third centimeters cubed, not 10 centimeters cubed. That's another mistake that students who are learning chemistry sometimes like to make. So let that stick with you, this object lesson. Cube the length as well as the volume when you're setting up your equality or your conversion factor. Now we already talked about how to take an equality and set it up as a conversion factor, but now we're really going to develop a more detailed problem-solving guide when you're confronted with the problems that I'm going to present to you in a moment. So it's always good to have a plan when you're looking at a kind of a word problem. You have to break it down and figure out in the step one, what is your given quantity and what quantity is needed or desired. Write it down. Always helps to write stuff down. Then 2 and 3 kind of go together. You need a plan to convert the given unit to the needed or desired unit. You also need to state the equalities and the conversion factors. Stating the equalities and the conversion factors might kind of help you figure out what the plan is. We'll talk about that more with a concrete example, but you need 2 and 3. You need 2 is going to say, oh, here's how I'm going to go from A to B to C, and 3 is the tools I'm going to use to get there. 4, if you've done 1, 2, and 3 properly, 4 is actually going to be the easy part. You just set up the problem and multiply things out so that things cancel, and if you do it right in terms of units canceling, you will get the correct answer. So if you look at this blue banner here, this is how you do it so that your given unit cancels and your desired unit is left in your answer. Now we're going to address a few problems, some unit conversion problems. How many pounds does 2 kilograms of cheese weigh? How many ml are in 0.5 quarts? On down the list here. You can use the table provided earlier in this presentation to figure out your needed equalities and then make those into conversion factors. I'm going to work through the first one, and then you can do the remaining 3 on your own as a form of good practice. How many pounds does 2 kilograms of cheese weigh? Now I call this a word problem, but obviously it's just a sentence, right? So there isn't too many complicating factors here. 2 kilograms of cheese is clearly our given quantity, and we're being asked to convert that to pounds. So that step 1 is our given and needed. Part 2 is setting up some kind of plan. How are we going to get from kilograms to pounds? So that's going to be kind of our ABC. 3 is, can we convert directly from kilograms to pounds? Are we going to have to go to grams, from kilograms to grams first and then get to pounds? So that will determine what our equalities and conversion factors are. And then finally, we're going to set up and solve, as I mentioned previously. So here is the solution, and a rather tasty and large chunk of cheese in the background here. So we're given 2 kilograms of cheese, and we need pounds of cheese. That's our step 1. Our plan is going to be going from kilograms to grams to pounds. Why do we have to concern ourselves with grams? Well, when you go back and you look at the conversion table, you're going to see that we have a conversion factor from grams to pounds or vice versa, but we don't have one going directly to kilograms. So we do, however, know how to get from kilograms to grams. So we're going to set up 2 equalities. 1 kilogram equals 10 to the 3rd grams, and 1 pound equals 254 grams. This will give us our conversion factors. Now the Thing is if we're going to go from kilograms to grams to pounds, we have to set up our conversion factors so that they cancel appropriately. 2 kilograms times 1,000 grams over 1 kilogram times 1 pound over 454 grams equals 4.41 grams. Study this for a moment. Does it look like units are canceling appropriately? Because if they don't, you're going to have to change things so that they do. Now, first, we see, yes, kilograms cancel because our kilograms are on the bottom in our conversion factor, and that's going to work with multiplying times 2 kilograms. Same thing for grams. Grams are on the bottom in our conversion factor, so we will cancel out our grams. We're going to be left with pounds. Yes, we have succeeded. If you set things up this way, if you're careful with your plan and writing things down rather than trying to do things too quickly and not thinking things through, you will have real success with doing these unit conversion problems.